I'm going to be going to the 02_units PowerPoint. These are all on files under the files section, so you can access them whenever you want. And so let's get right into it. Units and conversions. What time will it be in 3.5 kilograms? I think we all know that that doesn't make any sense whatsoever. Okay, your reading assignment to keep up with what we're doing in class. These are the sections of the book that you should be reading: 1.2, 1.3, 1.4, 1.7, and 1.8. And the examples in the book that I want you to be doing: 1.1, 1.2, 1.5, 1.6, and 1.7. You can read these sections and do those examples. It's the things that are literally labeled example 1.1, example 1.2, etc. You can do those, then you are keeping up with the class. So that is your assignment for right now. Units and dimensions. So what is a dimension? A dimension is a number that will tell you how much of something that you have. The question is the something. What is the something? And that what is the dimension? So the something has to be measurable, and you measure it with units. So the thing, you can measure money. You can measure how much money you have, but it matters if you're measuring it in dollars or euros or lira or something like that. So the money is the dimension, but the units is the currency. You can think of it like that. Obviously, we're not going to be doing very much with currency in this class. We will instead be doing things with length, with time, with mass, and next semester we'll be doing things with charge as well. This semester, length, time, mass. That's what we've got. Please, as we go through this, tell me as soon as you have a question. Sometimes I'll stop and ask for questions, but if you've got a question, just go ahead and raise your hand or go right into chat and start chatting. Dimensions and math. This is one thing, this is almost philosophical. The way that we talk about variables in math is often different than how we do it in physics. In math, A and B and C and X and Y and Z and any letter can mean anything. There's no preconceptions, let's say, when we're doing that kind of algebra in math. But in physics, these letters really mean things. A is acceleration, and V is velocity, and X is X displacement, and Y is Y displacement. And they can have subscripts on them. You can have like Vx, V sub X, which would be the velocity in X, things like that. And so beware of that as you are learning math and learning physics, many of you at the same time, learning taking those classes in school at the same time. And because it's easy to get a little bit confused going from a physics class to a math class. Each of these things will have their own units. So we'll talk about units in a little bit. Your displacement, that's going to be meters, your velocity, meters per second, acceleration, meters per second squared, etc. Okay, so now we've got things like meters per second squared, kilograms, meters squared per second. Those are units, or just plain kilograms or seconds. Those are units as well. We've got abbreviations for the dimensions here. So M is mass, T is time, L is length or distance or displacement, however you want to call it. V is velocity, A is acceleration. Those are the dimensions, but they can have corresponding units. A unit for mass, kilograms, unit for time, seconds, things like that. So that's the difference between units and dimensions. Let's see. There we are. We can make units from other units, as you probably already know. Velocity, that's a length over a time. Often I'll ask my students, what do you know about velocity? And they'll just, right off the top of their head, they'll say total distance over total time. That's totally true. You need to know the context for that, of course. But total distance, a length over total time, t, I guess. That's going to get you a dimension of velocity and a units of meters per second. Acceleration, on the other hand, is how quickly you're changing your velocity. It's how much your velocity is changing in a certain amount of time right there. So acceleration, is a velocity over a time. And if you look at the units for velocity, you just divide that by an extra time and you get L over T squared, which also gives you meters per second squared. This is going to be one of this is one common misconception, I think, in physics, understanding the difference between velocity and acceleration. Velocity is how many meters you're going through per second. And if I go 8 meters in 16 seconds, then I'm going 8 over 16, or 1/2 of a meter per second. My acceleration is how many meters per second I'm changing by every second. If I speed up from 0 to 10 meters per second in 5 seconds, then that means that I changed my velocity by 2 meters per second every second that elapsed. And that's going to be an acceleration. An acceleration is a change in velocity. Anyway, all these equations, anything has to have the correct dimensions. If an equation doesn't have consistent dimensions and units, it can't be right. And so I'm going to go and show some equations like these here, for example. Don't just assume that these are correct equations for any kind of situation. These are mostly just demonstrations of things. Here's a list of dimensions to look at, expressed as a combination of L, T, and M. Actually determine the dimensions of the following expressions, excuse me. Take these dimensions and determine their dimensions. These expressions and determine the dimensions. I'm going to give you actually maybe 3 minutes to go through this quickly and try to determine the dimensions of all these expressed as L, T, and M. So go ahead, spend the next 3 minutes looking at that. I'll give you the answers here. Determine the dimensions of all these things. Well, a velocity times a time. The velocity is a length over a time, so you multiply that by a time, you get a length. Mass over time, well, it's still just mass over time. That's not going to change anything. Acceleration times time. Acceleration is a distance over a time squared. So multiply that by a time and you get rid of one of the over times and you get length, just one length over one time, which is also equal to a velocity. Acceleration, length over time squared, times time squared, that just leaves you with a length. X over t squared, that's a length over time squared, same thing. Mass times acceleration, well, you still just got the mass, times the length over time squared, and many of you already know that's going to equal a force. It's good to be able to look at all that stuff and make determinations about what's going to be what in the units of that you're going to be looking at. Okay, any questions on this right now? All right, well, next slide. So we've got different kinds of things. We've got dimensions, which is what we are measuring, length, mass, time, charge. We've got units, which expresses how we measure it. So we've got things like feet and centimeters, which are two different length dimensions, or it's a length dimension, it's two different units that are measuring the length dimension. We've got seconds and we've got nanoseconds and we've got years and we've got months and things like that. That's all different ways of measuring time. We've got grams or kilograms or whatever. That's the different units for for a mass. A compound unit, things like meters per second, that's when you take different units and shove them together in various ways. Kilograms, meters per second squared, meters cubed, those are compound. Derived units, that's things that we have named. We've given specific names to some units, like newtons and joules. So you can name, these are compound units over here, but once we name them, we become a derived unit. And then, of course, we've got this absolute unit right there. All right, all my slides are just going to be like, I try to include some memes in my slides, but I never get rid of them when they get old. So my slides are one day going to just be archaeological digs of old memes, dead memes, and all that, but I will never get rid of them. Anyway, not that that matters. Using units in equation, or dimensions in equations, we need to always be consistent with all of our units and dimensions in the equations. You can't just say what time will it be in 3.5 kilograms, as we talked about at the beginning of the class, because time is not measured in kilograms. You can't say the brick is 17 seconds heavier than the rock. Again, that doesn't make any sense. You need to maintain consistency in the units and dimensions that you are using. So the rules are, when you multiply or divide, dimensions do not need to be consistent. You can take meters divided by seconds. That's totally fine. Meters divided by seconds, kilograms per meter cubed, those are totally fine because you're dividing or multiplying unlike units. You'll get just some different dimensions out of that eventually. But when you are adding, subtracting, or claiming equality, so like, this is equal to something else, then the dimensions must be consistent. So if you say, 5 seconds is equal to 2 seconds plus 3 seconds, yep, that's good. If you say that 5 seconds is equal to 2 seconds plus 3 kilometers, that's bad. That does not make any sense. So make sure that your equations are consistent in that way. Exponents on numbers have to be dimensionless. So you can take like 7 to the third power, for example, but you can't take 7 to the 3 kilogram power. That doesn't make any sense. The arguments of trig functions must have dimensions of either degrees or radians, and we'll talk about this a lot more later on in the semester. And the numbers themselves are dimensionless. Any questions on this? All right, well, you can't work with a neighbor. I thought I took out all these. You can't work with a neighbor on these, and I did not like the breakout rooms, so I'm afraid I'm gonna have to ask you to just spend a couple minutes looking at these expressions or equations and determining which ones are valid based on their dimensions. So go ahead and, okay. I'm seeing the chat right now. People are saying that they couldn't see the questions from there in the breakout room. Yeah, I totally get that, so we're not gonna do that. Go ahead and, and I see people talking about making a WhatsApp group. You can do that too. That is fine by me. Use those kinds of resources with each other as you can. In any case, I'm going to give you a couple minutes to look through these equations, and I'm just going to leave this up so that you can determine which ones of these are valid and which ones are not valid. You can do this on your own for now. Here we are. The green ones are good. X plus VT, well, VT just becomes X again. We've got V minus 2X over T. Well, X over T, that's going to be another velocity looking term. That 2 doesn't affect anything, so that's good. Adding 4 to a mass, well, that doesn't work because the mass might be measured in kilograms or in grams or in pounds. Well, not pounds, I guess. That's a unit of weight, of force, but take any kind of mass unit. You need to know what the units of that are before you can just add something to it. 5a is equal to 3/2 v. Well, that doesn't make any sense because the units of a and v are different and the numbers are all unitless. And then we've got this equation here, x is equal to vt plus 1/2 at squared. Then let's move on to unit conversion, another important thing that we'll need to use a lot this semester. Question for you. Ooh, would you rather have 100,000 Canadian dollars or 100,000 euros? You know what? Go to the reactions, and you know what? Give me a thumbs up if you want 100,000 Canadian dollars, or give me a clap if you want 100,000 euros. Oh, I'm seeing people just typing in clap. Okay. Ooh, it looks like people know their stuff. Good, good, excellent. Okay. Well, let's do the math behind this. There we are. Oh, see, I'm still getting used to my own slides. There we go. I guess that we already did that. So let's move on to this. Oh, yes. We can start by thinking about ratios between things. And let me see, do I have the papers that I need? We can think about ratios. If we know that two things are equal here, B is equal to C. If we know that B is equal to C, then we can divide both sides by C, and then we get B over C is equal to 1. And also C over B is equal to 1. But we know that we can just multiply anything that we want by 1, and it'll give you something equal to what you started with. You have anything in the world, you multiply it by 1, you still have 1, or you still have what you started with, I mean. So if you take some amount and you multiply it by 1, you'll have the same amount. What you can do is you say, oh, okay, I know that, let's see, B is equal to C. Well, if B is that 1 Canadian dollar is equal to C, 75 US cents, or 0.75 US dollars, then you can take one and divide it by the other, either 1 Canadian dollar over 75 US cents or 75 US cents over 1 Canadian dollar. You can multiply that by something else, and you're still going to have the same amount. And then you can keep doing that until you have the units that you want. You still have to make sure that the dimensions are right, but you should after having done that. So if this stuff is unfamiliar, then go ahead and go to the book, read section 1.4 of the book. I will, one thing I'm doing in these slides is showing you that picture again. I just had my my webcam looking at that sheet of paper, but I'm also going to just upload those as pictures into the PowerPoint slides. So you'll always be able to see all that stuff in these PowerPoint slides like that. So yeah, hopefully that works for everyone. I'll also have some random videos too. Another question. This is one, okay, I know how to get this one figured out. This one, I want you to calculate the speed limit on Babcock Street. The speed limit in miles per hour is 40 miles per hour. I want you to convert this into kilometers per hour, and I want you to convert this into meters per second. I'm going to give you some time to do this. I give you this big long list of conversions that you can use to make those, to do this problem. But I want you to try this out. As you can tell, I'm just trying a lot of different things today, seeing what works and what does not, for helping you to be able to work on this stuff during the class. But I want you to actually make these conversions, figure out what 40 miles per hour is in kilometers per hour and meters per second. And then when you have an answer, then you can talk about it in chat if you want, and you can calculate it. And then once you have an answer, use those answer buttons to show what answer that you have. And I'll give you a couple minutes to work on that too. So go ahead and start working on it. I just saw a good question in the chat. Do we have to memorize these, or will it be given? I will give you almost every conversion that you need. There's going to be some numbers that you need to memorize, but it's numbers like pi. Yeah, you need to remember 3.14 is pi, and you need to remember Yeah, eventually you'll need to remember that the acceleration due to gravity is 9.8 meters per second squared. And I might have you memorize that the density of water is 1,000 kilograms per cubic meter. Those things, yeah, I do expect you to be able to remember those. I expect you to be able to remember that 1,000 meters is equal to 1 kilometer, and 100 centimeters is 1 meter, and be able to make those kinds of metric conversions. But like crazy things like the number of feet in a mile, no, you don't need to remember that. And I agree with the next commenter that said that knowing the conversions will take you far. That is very true. You'll end up memorizing a lot of these conversions purely by accident because you'll use them so often. But not having to, go to Google and count and find the conversion yourself is going to be very convenient for you in the future. So yeah, just know them if you can, but if you don't, I'm going to give them to you anyway. So keep working on this problem. Answer with one of those response buttons when you can. I see them on the participants tab. So whenever I ask you to look at that, go to the participants tab and you'll see the list of reactions like that. Like I don't know if anyone can see it, but I can click yes, I can click no, go slower, go faster. And you can click those too. So go ahead and figure that out, and we will be back in a minute or so. Well, it looks like we're getting some good answers here. I'm liking what I'm seeing. Not everyone has answered yet, of course. That's okay, but yeah, the answer is the go slower one, which is 64.4 kilometers per hour or 17.9 meters per second. And I've got there's the answer. There is the work that you need. So if you ever need to understand why this works, you can go back to this slide. But we've got 40 miles per hour times 1.609 kilometers over 1 mile. That ends up being the conversion. I skipped over, maybe I shouldn't have skipped over so many conversions, but that is the conversion right there. And you can get rid of miles very quickly and then just multiply through. And then 1609 meters per 1 mile, you can multiply that by 1 hour over 3,600 seconds and then the 40 miles per hour, and you get 17.9 meters per second. We're off to a good start. Now, we've got unit prefixes. We were talking about this a little bit earlier, but here is a bunch of unit prefixes that you need to know. These I do expect you to, well, I'd say memorize, but because you'll have access to everything, you'll have access to all the books and all your notes and everything. Memorizing these I still recommend, but you'll at least have access to them on tests. So understand these, definitely know what these are and be able to actually use these on a test and understand how to convert. If I say that something is 48 micrometers or microns, then you'll be able to tell me how many nanometers that is, for example. Or something is a teragram, how many kilograms is that, or that kind of thing. Understanding those conversions is very, very important, I think. Oh, I do have a question from the last slide. Are these all the prefixes we should know, or do we need to know things like deci is 10 to the negative 1? No, you don't need to know deci is 10 to the negative 1. Okay, this building is at NASA, but what is the name of this building? Don't know the name, but it's where they build the rockets. Yes, they assemble them in there. Anyone? Oh, Vehicle Assembly Building. Yes, this is the VAB, the Vehicle Assembly Building. Yes, excellent. Okay, great. As soon as all this pandemic stuff is over, go up there and take the tour up there. The tour is fantastic. I really enjoy the NASA tour up there. It's expensive. It's like $58. to take the tour, but it's like you do stuff the whole day. So I really enjoy it. Anyway, let's do another question on the volume of the vehicle assembly building. Oh, and I ignore this. Ignore the use the squares thing. We need to find the volume of the vehicle assembly building, and that'll be a lot easier if I can find my piece of paper that has all the answers on it. And I don't know where that is. So I have a video on it. I think I misplaced that piece of paper when I made the video. Estimate the volume of the vehicle assembly building. Assume that it's a rectangular prism, 526 feet tall, 518 feet wide, and about 500 feet deep. Find the volume in cubic meters and give in scientific notation. And 1 meter is 3.28 feet. I only give you two possibilities. It's either going to be 4.15 times 10 to the 7 cubic meters or 3.86 times 10 to the 6 cubic meters. I want you to tell me what you think. Where do you think people are going to get this wrong? Can you look at this problem and tell me where you think, if someone gets it wrong, where do you think they're going to get it wrong? Type it into chat. Oh, okay, so one person said they won't convert to meters. Yes, you definitely need to convert to meters first. What you can do, there's two ways of doing this. If you want, you can take the 526, the 518, and the 500 and convert all three of those to meters first. And then you just multiply them together and you get your answer. Another way of doing it is to find out how many cubic feet the building is. What if you figured out how many cubic feet the building is? What would you need to do then? Divide by 3.28 cubed. Yes, that's what I was looking for. I have if you have something in cubic feet, then you need to get rid of the feet 3 times. I have a video on that. I give the answer here. So read section 1.4 if this isn't working in your brain. I also have a video here, which is, let's see if I can even do this. If I click this, I wonder if it's going to share automatically. Is it, can you see the YouTube right now? Type yes into chat if you can see YouTube right now. I'm getting no. Okay, then let me stop share. See, I'm still learning how this works. And then I can share screen again and then go there. Now can you see YouTube? I'm getting yeses. Okay, great, thank you. So I have this video. Oh, I really should not play the video while I'm talking. That is super confusing. In this video, I go through exactly all the steps to this. I actually made this video because I was not sure that I was going to get through everything that I wanted to get through today. It looks like we would have time to go through this manually, but this is the first day of class and I'm trying to test things out and see how it works. So I'm actually going to, someone is giving me advice on Zoom. That's useful advice. I'm actually going to not explain this during this class. I'm going to tell you, you need to go and watch this video to understand how this works. And, I made this video so that you can rewatch it. You see here, I'm dividing by 3.28 feet 3 different times. So it's 3.28 cubed down there. So watch this video, and I'll always leave these videos up for everyone to enjoy in the future. And let me see, was there anything else that I wanted to talk about today? Oh yes, there are some things that I need to talk about today. Let me go back to screen share. Nope. Right here. All right. Significant figures. We've got, here we are, significant figures. In this class, I'm not going to be too difficult on you for different numbers of significant figures. I know a lot of classes, they really, really care about the number of sig figs that you're using. I don't, just as long as you use like 3. Use 3 sig figs. and I'm going to be happy. You probably need to use like 8 sig figs in the middle of a problem. Just whatever your calculator says in the middle of a problem, use all that. And then at the very end of the problem, when you're reporting your answer, just use 3 or 4 sig figs, and that's going to be fine. Don't give me too few, because then, I don't know what you're talking about. If the answer is 2.49 and you just say 2, that's not specific enough. But if the answer is 2.49 and your calculator said 2.49027364,964, I don't care. I don't care about all that. Just give me 2.49. That's good enough. So 3 sig figs, that's all you need. I do give you some bonus problems in here, which we will not have time for. So on these bonus problems, it's more practice for you to go through. So look at this bonus problem, and I do give you the answer to this. So use these slides as much as possible as to your advantage in your studying. You can look at these bonus problems, try to calculate all these things. This is a fun one, in my opinion. What's the mass of an asteroid which is a radius of 3.5 kilometers, but express it in the terms of cruise ships? Because cruise ships, you can have these gigantic numbers, but it still doesn't make sense until you can express it in terms that other people can think about. And the answer, this 3.5 kilometer asteroid, that doesn't sound very big. Oh, but it's like more than 2.5 million cruise ships. That's absolutely insane. So these, I give a lot of fun bonus problems at the end that I will solve for you, but I won't necessarily give you all the work. So this is just to challenge you